Let us discuss the properties of DFT. The very first property is called as linearity. Linearity happens to be a very simple property. To consider the statement of linearity, we have to take two sequences called as x1 of n and x2 of n, having the respective DFTs given by x1 of k and x2 of k. Then the sequence, which is a combination of x1 and x2 in such a way that we are providing the scaled inputs, that is a times x1 of n added with b times x2 of n. Now this new input combination will produce the DFT, which is a scaled version of the respective DFTs, that is a times of x1 of k added with b times of x2 of k. Linearity basically is composed of two properties. One is scaling and second is superposition. To prove this, first we consider from the definition of DFT, we know that x of k is given by summation n lies between 0 to n minus 1 x of n times wn to the power of kn. First, let us consider the input x of n, let it be equal to x1 of n. Substituting in the definition of DFT, we obtain the DFT as capital X1 of k is equal to, here we have changed the input x of n to become x1 of n. Call this equation as equation 1. Next, consider the input, that is x2 of n, and in a similar fashion we call its DFT as x2 of k, which is obtained by taking the input, which is x2 of n in the DFT equation. Call this equation as equation number 2. Next, let us consider an input which happens to be a scaled and summed version of x1 of n and x2 of n. That is, x of n is a times x1 of n plus b times x2 of n. If we consider its DFT, then substituting in the definition of DFT, we are changing the input to be a times x1 of n plus b times x2 of n. Let's call this as equation number 3. And this equation could be split into two summations. The term a and b are constants, so they can be taken out of the summation because they are independent of the value n. Therefore, the equation is now expressed as a times the summation n between 0 to n minus 1 x of x1 of n times the total factor wn to the power of kn plus b times the summation that is representing the DFT of x2 of n. Now, since the individual summations happens to be the DFT of x1 of n and x2 of n respectively, hence they can be expressed as capital X1 of k and capital X2 of k respectively. Therefore, the answer is what is shown here. Now, from the equations 1 and 2, this is the result that we have expressed, and from this we can state that the DFT of a times x1 of n plus b times x2 of n is equal to a times capital X1 of k plus b times x2 of k. Hence the proof. The second property that we shall discuss is called as the periodicity property of the DFT. If x of n has a DFT, n-point DFT x of k, then x of n plus capital N is equal to x of n. This is possible only if the sequence x of n is periodic and has a period equals to capital N. Now, when this happens, the DFT is also periodic with a period of capital N. That is, x of k plus n is same as x of k. That means the DFT is also periodic. For periodic input, the DFT is also periodic. Or in other words, we can express x of n plus capital N has a DFT which is x of k. So x of k is same as x of k plus n. Hence we can say that the DFT is nothing but x of k. Now to prove this particular property, we're going to prove this last condition. So to prove that x of n plus capital N has a DFT x of k, once again let us take the DFT equation. When you consider the DFT equation, the DFT of x of n is denoted as capital X of k. It's given by the summation n between 0 to n minus 1 x of n w to the power of kn, where the value of k is going to range from 0 to n minus 1. Now in this definition, let us make the input x of n equal to x of n plus capital N. Other words, I am interested in finding the DFT of x of n plus capital N. So I am changing x of n to x of n plus capital N. Now on doing the substitution, we observe that DFT of x of n plus capital N is equal to, in the summation, in the definition, x of n has to be changed or replaced with x of n plus capital N. Okay. Now, after doing this, now we would want to simplify it. To perform the simplification, we could change the value n plus capital N and call it by a different name. Or let us say that n plus n is denoted as letter L. Therefore, from this we can obtain the value of small n to be equal to L minus capital N. Also, the limits which was previously defined in terms of n should now be defined in terms of L. To calculate the limits, first we consider the original limit n is equal to 0, substitute the value n is equal to 0 in this relation and solve for L. So we get L is equal to capital N. Similarly, the upper limit originally was n is equal to capital N minus 1. On substituting this value in the above equation, we get L is equal to 2n minus 1. So limits are calculated, the substitution for n is defined, the substitution for n plus capital N is called as L. Let us make all these changes in the above equation. Therefore, the summation now takes the form L between capital N to 2n minus 1 x of L, because L is the replacement for n plus capital N, Wn raised to k times L minus n. So this changes has taken place. Now, if we look at the twiddle factor, we observe that we can express it as a product of two terms. So it becomes Wn to the power of kl into Wn to the power of minus kn, and here simplification is possible. First, Wn to the power of minus kn happens to be equals to 1. This is equals to 1. We can prove it in a very simple way. So we can prove it in a very simple way if required. So we are aware that Wn is e power of minus j2 pi by n. We are interested in calculating Wn to the power of minus kn. Therefore, I will take the value of W of n and put the power minus kn. We observe that n and n cancels and minus minus makes it plus. So k value is an integer. So we are talking about integer multiples of 2 pi. As an example, let's consider k value is 1 for simplicity. Then the equation becomes e power of j2 pi. And we know the solution for that using Euler's relation is cos 2 pi plus j sine 2 pi. And the solution of that is 1 and sine becomes equals to 0. Hence we are very sure that the answer is equal to 1. Okay. So this twiddle factor will be solved. It will be substituted with 1. The limits is between n to 2n minus 1. It depicts n points. Now if the sequence itself is periodic, we can as well take the points between 0 to n minus 1 because it is repeating. Therefore, we change the limit to be between L is equal to 0 to n minus 1 x of L times Wn to the power of Kl. Now this equation resembles the DFT equation. So for your convenience, the DFT equation is also written here. We find almost all the terms the same except for the usage of L in place of n. Now since it's an index, it doesn't really matter what the index is called because the function will still be the same. Therefore, this is the same as a DFT equation. So we are calculating the DFT of x of L, which is nothing but x of k, and hence we have proved that the DFT of x of n plus capital N is equal to x of k. So this is periodicity property. The third property we discuss about is called as circular time shift. Up to now, probably we are aware of time shift which is performed linearly. Just to understand the difference between linear shift and circular shift, let's take a simple example. If we observe a sequence something like this, let's say the values are 1, 2, 3. If we are interested in performing a circular shift, it is treated like a rotate operation. That means that if I am shifting 1 unit to the right, the value 3 present here will not move further, rather it will come back to the first position and the remaining values will be shifted other side. So therefore, the shift will produce the combination 3, 1, 2. Like this, the process will continue. So how many places you want to shift? It is like you're performing a rotate operation. But you are aware in a linear shift what happens in the same case. When you shift it towards the right, the values will actually move towards the right. And multiple shift may eventually cause the values to become empty or be replaced by different numbers altogether. So we can think of the circular time shift to be like a permutation or a rearrangement of elements rather than an actual shift. Okay. So since it is circular, you might as well represent the point on a circle and consider rotating the values on the circle in the desired direction. So if you want clockwise, you can choose a certain direction. If you want anti-clockwise, you can choose a certain direction, indicating left and right shift operations. So this is how you can represent what is called as circular shift. So now, how do you implement circular time shift? The circular time shift operation on an endpoint sequence is denoted as x of n minus m, where we are shifting by m. The shift operation is under the control of mod. So we denote it as mod capital N. Alternatively, it could also be written as x double bracket n minus m subscript n. The double bracket signifies that we are applying mod operation. Or some literature also uses x of n minus m, comma, mod capital N. Now, the term mod is not a new term for you actually. Mod is used in different contexts. Sometimes mod indicates the magnitude, but here we are not using the word magnitude. Rather, we will just speak something about mod first. See, mod of n, when we apply, we should understand that the values that are possible for mod capital N should be between 0 to n minus 1. So it is obviously between 0 and 1 less than that number. So if I say mod 4, the numbers you will have is 0, 1, 2, 3. That is mod 4, or n value is equal to 4. Now, to consider more examples, binary is said to be mod 2 because the possible digits are 0 and 1. Decimal is said to be mod 10 because the digits are 0 to 9. Hexadecimal is said to be mod 16 because the digits are between 0 to 15. So let us now take an example how mod actually works and how you calculate using mod. So for example, you have 4 mod 3. The value 4 is more than 3. But we know under mod 3, the permitted values are 0, 1 and 2 only. Therefore, to correct the number, we subtract the value 4 by that n is 3 here, no? 4 minus 3 gives you an answer which is 1. One more example. So this one is in the range, so this is fine. Now if you take the value 8 mod 3, subtracting 1s gives you a value 5. Is the 5 in range? No, obviously not. Therefore, we once again subtract with 3 and the answer is 2 and that is in the range, so that's the answer. So the concept is very simple. If the number is positive and it's a value greater than n minus 1, you can repeatedly subtract with n until you get the answer. Now coming to negative numbers, when we say minus 1 mod 3, to make it positive, obviously we cannot subtract, we have to add. So this time we add the value n. So minus 1 plus 3, answer is 2, which is once again in the range. So this is the method of application of mod and how you can apply mod to reduce or solve the value. Okay. Now, mod is also sometimes referred to as the remainder of division. Okay, 4 divided by 3, quotient is 1, remainder is 1. So this is thought of as the remainder of a division. Now, let us talk about the property which is called as circular time shift property. It's a very simple property, but it's a very useful property also. The statement of circular time shift property is something like this. If x of n has endpoint DFT x of k, then x of n minus m, so we are shifting it by m, and then we are applying mod. So the double bracket indicates that shift happens circularly. So this is called as circular time shift. Now what happens in the frequency domain? So its DFT is nothing but x of k into e power of minus j2 pi by n into km. So if you look at the expressions on both sides, what you observe, the negative sign may be assumed to be performing a right shift operation. So when we see minus here, the power of the exponent is also minus. And we have the exponent, as you know, which looks very much like your total factor e power of minus j2 pi by n. And then we have in the DFT equation, we use a word called as kn, the term. Now here we have k times the shift. So the magnitude of the shift is given by m. The sign is negative. Now since it looks like the total factor, we can actually express it as w of n. Then the same could be called as x of k into wn to the power of k times of m. Now when you're writing it in the w of n form, please note the sign. Previously we said the signs were matching, negative with negative, and the magnitude was given by m. Now what happens to the sign for the wn? It will be opposite. So if you have minus here, please remember it will be plus over here. Okay, and again the amount of shift is nothing but m. So we have km as a power. So we can remember this property in this fashion. Automatically it is implied that if the sign here is changed, the sign in the exponent and the total factor form will also change accordingly. Okay, so let us go with the proof now. First, let us note down from the definition of DFT, we have x of k given by the expression of DFT, and we are interested in calculating the DFT of x of n minus m mod n. Therefore, I am going to replace x of n with that value. So putting that value here, we are calculating DFT of this value, which by application of the formula of the DFT or the definition of DFT, we are changing the input to be x of n minus m mod n. Now to perform simplification, what we have to do, we take that n minus m and replace it with L, and that should change the value of n to be L plus m. We compute the limits also. We calculate the value of the new limit L by substituting the value of the old limit and solving the equation. we get the limits as L is equal to minus M and L is equal to N minus 1 minus M. This can be checked very simple way by solving it. Now, substituting all these things, the lower limit is L is equal to minus M, the upper limit is capital N minus 1 minus M, x of L mod N, Wn to the power of k times L plus M. This is what you get by doing simple substitution. Now from this, what you can observe here is that once again, if you count the number of points, it is n. Now here you can use periodicity once again and change the limit to be between 0 to n minus 1 because we are talking about a periodic sequence here. So it's a periodic one, so it's good if you can consider range from 0 to n minus 1. Now this can be simply called as x of L because we know we are guaranteed that the L value will be in the range 0 to n minus 1, hence you can simply call it as x of L. Twiddle factor is split into two terms, Wn to the power of kl into Wn to the power of km. Then the highlighted quantity here, it again has a structure similar to the DFT. So since the input is x of L, it can be represented as capital X of k multiplied by the extra term which is Wn to the power of km. Hence we have proved that the DFT of x of n minus m mod n is equal to capital X of k times Wn to the power of km. Let's take up a simple numerical based on this property. If you are given a sequence x of n with the values 1, 2, 2, 1, find the DFT of the sequence y of n which is equal to x of n minus 2 mod 4. So clearly we see that y of n is obtained from x of n by performing circular time shift. And since we are interested in finding the DFT of y of n, we have to apply the property called as circular time shift property. Okay. First task for us before we apply circular time shift property is to compute the DFT of x of n. So we know by applying the formula or using matrix method, we are capable of solving the DFT. If you solve it, the answer we get will be something like this. Solution is left as an exercise for you people. So the answer is 6 minus 1 minus j, 0 minus 1 plus j. Now, since the problem states that the relation between y of n and x of n is this, if we apply the DFT on both sides, then it becomes y of n's DFT is y of k, x of n minus 2 mod 4. This is from the circular time shift property. We are aware the property is x of n minus m mod n. DFT is x of k times Wn to the power of km. Accordingly, we observe that the m value here is 2. N, capital N happens to be 4. Therefore, the DFT of it is capital X of k times Wn, which is 4, raised to k times of m. So it is k into 2 or can be written as 2k. Now, since we have 4 inputs, we may require to get a 4-point DFT. Hence, we have to solve for k is equal to 0, 1, 2 and 3. So when we apply the different values, let's say k is equal to 0, the expression becomes y of 0 is equal to x of 0 into w4 to the power of 0, and we substitute the value of twiddle factor. W4 to the power of 0 is equal to 1, hence the answer is 6. Similarly, k is equal to 1, it gives you y of 1 is equal to x of 1 into w4 to the power of 2, and substituting the value of w4 to the power of 2, which is minus 1, along with the value of x of 1, simplify, we get the answer as 1 plus j. When you put k value is equal to 2, y of 2 is equal to x of 2 into w4 to the power of 4, and substituting here yields an answer 0, and k is equal to 3 is nothing but y of 3 equals x of 3 times w4 to the power of 6. Using periodicity of twiddle factor, we know the value w4 to the power of 6 is same as w4 to the power of 2, and the answer we know is minus 1. So multiplying it and simplify, you get answer is 1 minus j, and we can list out the result y of k is equal to first value is 6, second value is 1 plus j, third value is 0, and fourth value is 1 minus j.
Thank you all.